Hey everyone, welcome back. Today, we are venturing deep beneath the surface for a brand new explainer, looking at the incredible planetary machinery that drives earthquakes. Demystifying earthquakes, from planetary engines to sudden snaps. Now, we all know earthquakes demand our respect, but today we really want to look right past that surface-level destruction and get into the actual geophysical mechanics, that immense, mind-boggling release of energy happening miles below us.
You know, for centuries, humanity was completely baffled by earthquakes. What makes solid ground suddenly and violently shake out of nowhere? Well, according to ancient Japanese mythology, the tremors were caused by Namasu. He was this giant mythical catfish who supposedly carried the entire island of Japan on his back. The story goes that a demigod was tasked with holding a heavy stone over Namasu to keep him still, but whenever that demigod got distracted, the catfish would thrash around, and boom, the earth would tremble. It's a really cool myth, but modern seismology reveals that the actual physical machinery driving these tremors is way more complex, and honestly, way more fascinating than a restless giant fish.
So, here is our roadmap for today. 1. Earth's shifting tectonic plates. 2. Types of plate boundaries. 3. The elastic rebound theory. 4. Seismic waves and shaking. And 5. We're going to wrap things up with some really interesting earthquake facts and FAQs. Let's dive right in. Section 1. Earth's shifting tectonic plates. Okay, let's start with the big picture. To understand just a single earthquake, we first have to look at the entire Earth as this massive, churning internal heat engine.
Now, the ground feels pretty static to us as we walk around, right? But the lithosphere, that's Earth's rigid outer shell, is actually fractured into a giant jigsaw puzzle of massive tectonic plates. And because they're being driven by this incredibly intense heat churning in the mantle right below them, these plates are in a constant state of reorganization.
But the absolute most crucial point here is just how incredibly slowly they are moving. We are talking about 2 to 5 centimeters per year. To put that into perspective for you, the massive, heavy continent you're living on right now is drifting at roughly the exact same speed that your fingernails grow. Literally. It's totally imperceptible to us as we go about our day, but over millions of years, that slow drift completely reshapes the entire globe.
Moving on to Section 2, Types of Plate Boundaries. So the interiors of these massive plates are actually relatively stable. The real action happens right at the edges. Let's look at where these plates actually touch and interact. There are basically 3 main types of plate boundaries, and their specific motions totally dictate the type of earthquakes they produce. First up, you have divergent boundaries. This is where plates pull apart, driven by tensional stress. It creates brand new crust, but usually only gives us shallow, moderate earthquakes. Next are convergent boundaries, where plates violently crash into each other. This compressional stress destroys crust, usually by shoving one plate right underneath another in what's called a subduction zone. This is where you get the absolute deepest, highest magnitude earthquakes on the planet. And finally, transform boundaries. This is where plates slide laterally past one another. The crust isn't created or destroyed here, but the intense shear stress creates shallow, very high magnitude shaking.
Let's put some real-world names to these. The Mid-Atlantic Ridge is a classic divergent boundary, pulling apart deep under the ocean. The Himalayas? They were actually formed from a massive convergent collision when 2 huge continental plates just slammed together. The Mariana Trench is another convergent example, but it's an extreme oceanic subduction zone. And of course, the San Andreas Fault in California is your textbook example of a transformed boundary. That's where the Pacific Plate is just constantly, relentlessly grinding horizontally to the northwest past the North American Plate.
Section 3. The elastic rebound theory. Okay, knowing that plates move past each other is one thing, but why does that super slow, constant motion result in sudden, terrifying earthquakes instead of just a smooth glide? Let's zoom in further to the local scale.
Following the catastrophic 1906 San Francisco earthquake, a scientist named Harry Fielding Reid literally changed geology forever. He went out, surveyed the land, and realized something profound. The shaking wasn't the cause of the rock breaking, it was the exact opposite. The breaking of the rocks was a sudden release of pent-up energy, and that energy release is what caused the shaking. He called this the elastic rebound theory.
Picture it like this. You've got a fault line where high friction causes the plates to get completely stuck, or locked, together right at their edges. However, the massive plates miles and miles away from that fault are still moving. So the solid rock right at the boundary starts to physically bend and deform elastically. It's literally storing up immense strain energy over decades or even centuries, exactly like a giant rubber band stretching tighter and tighter. Finally, the strain is just too much. The fault violently ruptures, the rocks snap back to their original unstrained positions, and boom. That snap is the earthquake.
This gives us what scientists call the seismic cycle, which is broken down into 3 distinct phases. First is the silent, sneaky phase, interseismic locking. This can last centuries, where the fault is stuck tight and accumulating strain. Second is the main shock. That's the violent rupture and elastic rebound that takes just seconds but causes total chaos. And finally, we have the aftershock sequence. This phase can last for months or even years as all the surrounding crust shifts and grinds to redistribute that newly altered stress field.
Section 4. Seismic waves and shaking. So the fault has snapped miles underground, but how exactly does that localized fracture translate to your house shaking off its foundation? Let's get into the physics of seismic waves.
When that underground snap happens, the energy blasts outward in a few different types of waves. The very first to arrive are the primary waves, or P waves. Think of them kind of like sound waves. They're push-pull compressional waves that can blast through basically anything: solid rock, liquid, or gas. Then, a bit later, come the secondary waves, or S waves. These shear the rock from side to side. But here is an absolutely mind-blowing fact for you. S waves physically cannot travel through liquid. Because seismologists noticed a massive S-wave shadow on the exact opposite side of the globe after major earthquakes, it provided the definitive slam-dunk proof that the Earth's outer core is actually made of liquid iron. I mean, how cool is that?
Now, while those P and S waves travel deep through the body of the Earth, which is super helpful for seismologists trying to locate a quake, they aren't usually what knocks down buildings. The real trouble starts when those deep waves interact with the surface and create surface waves, specifically Love and Rayleigh waves. Rayleigh waves actually roll the ground in an elliptical motion, almost exactly like ocean waves. They show up absolutely last to the party, but they carry the most energy and cause by far the most significant destructive shaking.
Section 5. Earthquake Facts and FAQs. All right, we've covered the mechanics from the planetary scale all the way down to microscopic waves. Let's transition to our final section here and rapidly clear up some incredibly persistent myths, using official data straight from the U.S. Geological Survey. You've almost certainly heard a lot of these before. First up, time of day or earthquake weather. Totally a myth. Because earthquakes are driven by massive tectonic forces miles below us, they're equally likely to happen in the morning, at noon, or the dead of night. Second, people always ask if a tremor is a foreshock. The truth is, foreshock is a completely relative term. You can only label it a foreshock after a larger main shock hits the exact same location. Third, despite what you see in every disaster movie, the ground doesn't usually yawn open into a bottomless chasm to swallow the bad guy. In fact, not all earthquakes even break the surface. And finally, depth is absolutely critical. A massive earthquake 500 kilometers deep might barely rattle your windows, while a moderate one just 20 kilometers down can be completely devastating because the surface waves just have way less distance to lose their energy.
We've literally and figuratively covered a lot of ground today, from giant mythical catfish to the elastic bending of solid rock. So, I want to leave you by connecting this incredible science right back to your immediate reality. What do you think is happening beneath your feet at this very moment?
The reality is, the Earth's engine literally never stops. Right now, miles beneath wherever you are sitting, immense, invisible stress is slowly building. Massive tectonic plates are silently sliding, colliding, and locking together, all at the exact relentless speed that your fingernails are growing. It is such a humbling reminder of the dynamic, living, breathing planet that we call home. So what other invisible forces do you think are shaping our world right beneath our noses? Something to think about. Thanks for joining me on this explainer, and until next time, keep exploring.